is going to be a quick lesson where we look at a few examples of predicting molecular compounds using bonding capacity. So there's a few steps we need to remember. First, identify the bonding capacity of each element present. Second, use the one with the highest bonding capacity as the central atom. 3, place the remaining atoms around so that each thing meets its bonding capacity and has a full octet. We will need to, in some cases, also add double bonds or triple bonds or ring structures. So that tends to be more of an exception, but it does happen. The ring structures tends to be more of an exception, but it does happen. So looking at our first example here, we have hydrogen and silicon. So first we need to look at what bonding capacity they each have. So hydrogen, remember, is in group 1. And if you don't remember, always look in your periodic table. And silicon, again, if you look in your periodic table, is in group 4. So it has 14, I should say, but has 4 valence electrons. So if we look at their bonding capacities, hydrogen has a bonding capacity of 1, and silicon has a bonding capacity of 4. So silicon has the higher bonding capacity, it's going to go in the middle. And hydrogen tends to be one of our easier ones because it always forms one bond, so it's always what we call terminal. It's one of the end atoms. So we surround the silicon using its 4 bonds with the hydrogen. And we can see in this case that we don't need any more electrons, even if we're drawing a Lewis structure where we're showing lone pairs, because hydrogen has no lone pairs, silicon has no lone pairs. We can also see silicon has a nice stable octet, 2, 4, 6, 8 in those bonds, and hydrogen has a stable duet, right? Each only has 1 bond and no lone pairs. So it meets those criteria for stability. So this question also asks us to write a balanced formation reaction. So we have silicon, which is just silicon, Si. Hydrogen, which we need to remember is diatomic, forming hydrogen, which sometimes hydrogen silicide, which sometimes gets shown as silicon hydride, because hydrogen being an exception, sometimes we will see it both ways. So to balance this, we have 4 hydrogens because we had 4 in our structure. 1 silicon. On this side we have 1 silicon and 2 hydrogens, so we can match that up by putting a 2 here. Okay, moving on to example 2, we have nitrogen and chlorine. So same thing, we look up each substance, each atom. Nitrogen has 5 valence electrons because it's in group 15. Chlorine has 7. So we expect nitrogen to form 3 bonds and chlorine to form 1 bond. So if we show the nitrogen with 3 bonds, doesn't matter which directions we put them, but going around the sides, and we put the chlorine around, and we can see now each nitrogen has 3 bonds, each chlorine has 1 bond, so they each are meeting that bonding capacity. If we were just drawing a structural diagram, we can stop here. If we want to show this as a Lewis diagram with all the lone pairs, we can add in that extra lone pair that nitrogen has on it, and for each chlorine we would add in 3 lone pairs. So we need those if it's a complete Lewis diagram, but we don't need them if it's just a structural diagram. Now the nice thing about putting them there when we talk about shapes, we can see the lone pairs, and that sometimes helps when we talk about the shapes of molecules. So there we go. We've got nitrogen with 3 chlorine, or nitrogen trichloride. So our formula for this one in the formation reaction, remember nitrogen's diatomic, chlorine is diatomic. This new structure has 1 nitrogen and 3 chlorines, nitrogen trichloride, And so it's not balanced because nothing here is working out, right? We have 2 nitrogens and only 1, so we can do this to make it so there's 2 nitrogens, but now we have 6 chlorine, so we need a 3 here to balance out our 6 chlorine. So there's our balanced formation reaction between those two. Our last one is one of these ones that's a little bit tricky. So if we look at carbon, group 14, so it has 4 valence electrons that can form 4 bonds. Selenium's in the same group as oxygen, group 16, so it's got 6 valence electron and can form 2 bonds. So if we try and show this one with carbon having 4 bonds like this, the problem we end up with, so this isn't right, but we're just doing it to show, the problem we have is that, well, carbon would be happy like this, but selenium's not working out because it only has 1 bond each. Now, you might think, okay, maybe I can attach my selenium like this, but that's highly unusual, not just a little bit weird, so we wouldn't do that. And in fact, we wouldn't have 4 selenium. Because another way we can make the carbon happy is by putting in double bonds. So we can put in a second bond here, so now each carbon has 4 bonds, or a stable octet. Each selenium has 2 bonds, which it likes, because then those 2 lone pairs, 2 lone electrons, pairing electrons, become paired in those bonds. And it does have each selenium 2 lone pairs. So if we're counting up electrons, 2, 4 in our lone pairs, 2, 4 in our bonding electrons, so a total of 8 around each selenium. So this you might recognize as looking a lot like the carbon dioxide, because selenium and oxygen are in the same family, and it makes sense that they end up having similar structures. So the formula now for our balanced equation: carbon, just atomic, plus selenium, again, we can treat that as just atomic, forms carbon diselenide. So to have 2 selenium in the end, we need 2 selenium in the reactants. And there's some quick examples of predicting molecular formulas using bonding capacity.